Hi, my name is Trevor Best. I am the CEO of Syzygy Plasmonics. So the traditional chemical industry has remained largely unchanged for the past 100 years. If you want to make chemical or fuels, first you take some kind of feedstock. This is traditionally a fossil fuel like naphtha or natural gas, and you burn it to produce heat. That heat is used to power an enormous chemical reactor. Imagine a refinery in your mind. These are huge structures. Those reactors are heated to more than 1,000 degrees Fahrenheit, and then the products that are made, things like fertilizer, fuel, raw materials for plastics and other things, those are delivered to the point where they're finally consumed. Now, there's three big problems with this business model. First, burning that fossil fuel feedstock to produce heat is responsible for gigatons of carbon emissions every single year. Second, while everybody wants emissions reduction, it's very, very difficult to stay competitive if that emissions reduction doubles or triples the cost of your products. And finally, the centralized production model is really starting to show its age. Many industries are successfully decentralizing today. You see it happening in power with microgrids. You see it happening in manufacturing with 3D printing. You see it happening in medicine, where you can now see your doctor online instead of having to go to the hospital. Chemicals is no different, and there are many opportunities for these industries to reduce their carbon emissions, maintain their cost competitiveness, and move to decentralized models. So why is Syzygy's photocatalyst interesting when compared against traditional thermal chemistry? That is because we drive our chemical reaction with light instead of heat. The heat means that you need a lot of very expensive materials. So high temperature, high pressure means you have to build everything out of nickel and chrome, means very intense engineering requirements and system components to manage that pressure and temperature. Syzygy's photocatalyst, however, operates at much lower temperature. This means that we can build our reactor out of completely different types of material. Think about aluminum and glass. Also the engineering requirements for our system are much less because we aren't dealing with pressure or temperature in the same ways. So this allows us to greatly reduce capital expenditure versus traditional infrastructure. In addition to this, it also enables a number of interesting abilities for Syzygy. One good example would be the start, stop, and maintenance of our reactor. So because we're using light, it is quite as simple as you turn the lights on and the reaction starts, and you turn the lights off and the reaction stops. This means that if you want to start or stop your chemical reactor, you can do that in a matter of minutes, compared with more than 24 hours for a traditional thermal chemical reactor. This makes maintenance and operation much, much simpler and helps to reduce the operating costs. So when you eliminate the combustion stream, you eliminate approximately 40% of the emissions that are created from the steam methane reforming process. The work that Syzygy is doing is not the first time that researchers have dug into plasmonic metallic nanoparticles. In fact, for the past 2 decades, many researchers have been creating plasmonic type photocatalysts. Syzygy is unique in that we are the first ones to make these structures in a very specific way. We call it the antenna reactor photocatalyst, where we are physically coupling the plasmonic nanoparticle with the antenna reactor. Displays an order of magnitude increase in many of the aspects that are important for chemical engineering. For example, catalyst activity. It has very, very high activity, not only for a photocatalyst, but it also has higher than usual activity when compared against thermal catalysts. It also has unusually high stability. That means that it is highly resistant to catalyst degradation from coking, oxidation, and sintering. The antenna reactor photocatalyst also displays very high efficiency. Because of the tunable plasmon, we are able to tune it against the light source so that it is an extremely good light harvester. And then because of the antenna reactor nature, the plasmonic nanoparticle with the catalyst particles on the outside, all those photons that are coming in, we are actually able to direct them to the catalyst to use them very effectively. This makes it the world's most stable, most active, and most efficient photocatalyst to date. The targets that Syzygy is most interested in are hydrogen to begin with, followed by CO2 processing, then fertilizer production, which is ammonia synthesis, and finally, ethylene. We are already scaling our hydrogen production technology. We have accomplished bench scale for CO2 processing and plan on continuing to scale that. We are still in fundamental R&D for ammonia synthesis and other chemical reactions like ethylene, and those will be coming later.